Hi everyone, welcome back. I hope you're having a wonderful day wherever you are in the world. So we've been talking about how to define a set. So what I want to talk about today is how to define a set of numbers. So there are some special pre-built, pre-packaged sets of numbers that we can get started with. And the sets of numbers that we're going to look at are Z or Z, the set of integers, Q, the set of rational numbers, and R, the set of real numbers. Now, those are just a few of the special sets of numbers. There's also complex numbers or natural numbers or irrational numbers, but we'll talk about them in a later video. Okay, so Z is the set of integers. So what is an integer? So an integer is a whole number, and that means no decimals and no fractions. So the set Z or Z is infinitely big, and it would stretch on forever and ever until positive infinity on one side and forever and ever till negative infinity on the other side. Okay, the next one is Q. So this is the set of rational numbers. So what is a rational number? So a rational number is any number that can be expressed in the form A over B, where both A and B are integers, and B isn't zero, because you can never divide a number by zero. So every integer is also rational. So why is that? So we can express any integer in the form A over B by simply just dividing the number by 1. But we can also get numbers which aren't whole numbers. So something like, 3 over 5, 4 over 9, negative 17 over 20. So any fraction where both the numerator and denominator are integers. So Q is also infinitely big. So first of all, because it contains all the elements of the set Z, which is also infinitely big. But beyond that, there's also an infinite amount of numbers between all the integers. So for example, let's think about all the numbers that exist between 0 and 1. So there's 1 over 2, 1 over 3, 1 over 4, 1 over 5. And we could just keep going and going and going until we get to an infinitely small number, getting closer and closer to 0. Okay, finally, we have the set R, the set of real numbers. So we can think about a real number as any distance along the number line. So any possible value which could exist along an expanse of the number line. Now, all the numbers in Z and Q, so all the integers and all the rational numbers, are also real numbers, because a length along the number line could be an integer or it could be a rational number. But beyond that, in R, we also have what are called irrational numbers. So these are numbers that cannot be expressed in the form A over B. So for example, we could have pi, we could have root 2 or root 3 or root 5. Lots and lots and lots of those numbers, they're called irrational numbers, numbers that cannot be expressed as A over B. Okay, so to sum up, we have Z or Z, which is the set of integers, so the set of whole numbers. Q, the set of rational numbers, so any number that can be expressed as A over B, where A and B are both integers and B is not zero. And R, the set of real numbers, which represents any distance along the number line. Another thing you might see is these letters with a superscript plus sign or a superscript negative sign. That means we're just restricting our attention to the positive numbers or the negative numbers. So for example, if we had an R with the superscript positive sign, that would mean we're just talking about the positive real numbers. Another thing you might see is a superscript non-neg. That just means the positive numbers plus 0. Okay, so what if we want to define a specific set of numbers? So for example, the set of real numbers between 5 and 10, or the set of rational numbers between negative 17 and 3. For these kinds of sets, we need to use what's called the set builder notation. So let's have a look at that. So the set builder notation is based on the idea that we take elements out of a bigger set and we put them in a new set based on whether or not they meet a certain condition. So a really useful metaphor I like to think about, you know those signs which are in the front of a roller coaster that say you must be this height to get on the ride? It's basically the same principle. So the roller coaster sign is giving us a test. So whether or not you are taller than 5 foot, let's say. So let's have a look at the notation. This would be our set of people that can go on our roller coaster ride. So we still have the curly brackets from the set roster notation, but now we have a variable x, and this stands for all the possible elements which can or cannot go into our set. Then we separate the variable from the rule with this vertical line, and then for each of the possible elements, we test whether or not they meet the condition which we define on the right side of the vertical line. Now, usually when we use the set builder notation, we have to specify where the possible elements come from. So for our roller coaster example, we would update our notation by specifying that X has to come from the set of people who are at the amusement park. Now, when we are talking about numbers, we would put our special predefined sets of numbers in this slot. So things like Z, Q, or R. So for example, if we want to define the set of integers between 2 and 7, let's say, we would write it like this. So it would be the set of X from the set Z such that X is between 2 and 7. So let's look at a few example questions.
What elements are in the following sets? So X is in R, so a reminder that R is the real numbers, and X is between 4 and 10. Okay, so it's going to be way too hard to list all the real numbers, so let's write it on a number line instead. It's going to be an interval between 4 and 10. Now we're going to use open circles to mark the boundaries of the interval. The open circles mean that 4 and 10 themselves are not included in the interval. Okay, so that would be the interval of elements in this set A. Okay, let's look at the next one. So X is in the set integers, and it is between -4 and 2. So -4 won't be included because X has to be strictly larger than -4, but we'll have -3, we'll have -2, -1, 0, and 1. Again, 2 won't be included because X is strictly less than 2. Okay, so that would be our answer for B. Now, C is just the same as B. There's only one difference. The only difference is this a superscript positive sign. That means we're just restricting to the positive integers. So the integers where X is above 0. So it'll just be the same set as B, except only the positive integers. There's only one positive integer, namely 1. So this set will only have one member in it. It'll be the set containing 1.
Okay, so let's look at this example. Which of these sets are equivalent? And we've got 4 different sets here. So, okay, let's look at the first one. So X is from the set of integers, and X is between 0 and 11. So X is greater than or equal to 0, so 0 will be included. And then we got 1, 2, 3, and then all the way up to 10, not including 11, because X is strictly less than 11. Okay, looking at B. So X is from the set of real numbers, and moreover, it is from the set of positive real numbers. Any element in this set has to be greater than 0. X has to be between -5 and 11. So because we're dealing with real numbers, this has to be some kind of expanse along the number line. So going from -5 to 11. Because we have this plus sign here, we're only dealing with numbers that are greater than 0. Only the numbers which exist along this expanse. Okay, so we can pretty clearly see that A and B are not equivalent. One reason being that B is an infinitely big set, while A is not. So A does not equal B. Okay, let's look at C. X is a element of the non-negative integers. So that's the positive integers plus 0. Okay, so X is greater than -1 and less than 11. So it will include 0, 1, 2, 3, and then all the way up to 10. Again, it's not including 11 because it's strictly less than 11. Okay, so we can see that these two are equivalent. So A does equal C. Okay, looking at the last one, X is a real number, not necessarily a positive or a non-negative real number, just a real number. And X is between
0 and 11. Okay, because we're dealing with real numbers, we again have to go along the number line. We are going from 0 to 11, not including either. That's why we have these open circles here. And then it's any number that appears on this expanse. So you can see that it is exactly the same as our example in B, right? Because it's all the real numbers between 0 and 11, not including 0 and not including 11. So B equals D.
All right, that's about it from me. Thanks so much for watching. Thank you for subscribing. Thank you for liking. And I will see you next time. Bye, everybody.